Go deeper into the generalized least square estimation procedures. So remember in the first chapter, most of the time we talked about linear regression model under standard assumptions, so weak or strong exhaustion of regressors, and in particular homoscedastic errors in repeatable operation, right? So before we go to the generalized least square settings in chapter 7, let's spend a few slides about non-linear regression, because that was one of the restrictions, so to say, we talked at the very beginning of the lecture that, well, we talked so much about the linear regression model, although the world is so complex and non-linear out there, okay? So, and we already said, well, okay, if you can just transform the variables, right? You can run linear regression with sine, cosine, square root of a variable or whatever, and that's still linear regression then. Okay, this is one thing. But the other thing is that, of course, you can deal with that in a more general way if you know, under the assumption that you have some clue about the functional form. So you see here a regression model. This is still our endogenous variable that we want to explain. It depends on some exogenous variable x. Here it's only one, but that's just for convenience. And we have a vector of unknown parameters that somehow determine that functional form. Okay, so suppose you know that it's some polynomial of order, I don't know what. Or it's a complicated function of, I have here an example, look, it could look like that. It is, you know that it's somehow an exponential function that drives the relation between x and y, but you don't know exactly, all these parameters that shape this function. Okay? So this is a world we're now looking at. So we have some clue about the function form f, right? This is not too unrealistic, right? But it depends on a vector of unknown parameters, and this is the vector we want to estimate now. And the ideas of non-linear least square is that we follow exactly the same logic as in linear regression model. So we try to fit the beta, we try to choose the beta in a way such that the square deviations from the forecasted or predicted values, the fitted values of the model, and the actual observations of y, that these sum of squared residuals, so to say, are meaningless. Okay, that's why it's called non-linear regression, or non-linear least square estimate also. Right? So that's a function, and if you just, if you assume you know the functional form f, then you can just, morning, take the first derivative, right? It's a function, it's a multivariate function, it depends on several variables, so you know what to do. the gradient, so the vector of first order partial derivatives must be 0 to the first order, etc. So this is all standard, right? And well, that's a square, so it's 2 times, or minus 2 times the inner derivative times the outer derivative. So this is the first order condition of nonlinear. Okay? And if you think that f is actually a linear function, so then of course this is we're just back to the first 5 chapters of the lecture. So this is really a generalization of the linear regression model. Okay. The problem is now if this is not, in the linear regression model, the first derivative of a linear function is a constant, right? But here's just a constant, and then it's a linear equation, and we can solve it by matrix multiplication and so on. Right? This is what we did in the first 5 chapters. Now it's probably not constant. If f is non-linear, then it depends on x and who. Difficult, right? It's not so easy to solve analytically. And in fact, if you do nonlinear regression or nonlinear least squares, you have to solve this equation numerically. And so the computer does it for you, right? And we'll say 2 words later on how the computer does it in principle. Okay? So this is why if you type in your statistical software program, please solve with nonlinear least squares, then there will be some iterations. Right? Then it will, of course, it will be quick because it's a fast computer, hopefully you have, right? But if you look, it will always be information, convergence achieved after iterations. So it's not like in the least square model with a linear regression model that there's an analytical solution. So it's just an equation that's solved, bam, and there are no iterations. It's just here it is, right? But it's an iterative process. Okay. So before we talk about more how exactly this is done and what are the properties of that estimator, a few words about identification. Identification is when you're doing microeconometrics next semester, probably, or if you're doing time series analysis next semester, probably, then identification is a big issue. It tells you, well, is it really possible to estimate the parameters I'm really after? Right? And identification means that, well, I want to distinguish between this parameter vector and that parameter vector. If I can't distinguish between them, they're not identified. Right? And I cannot distinguish between, or put it the other way around, they are identified. I can distinguish between those two if I find a data vector where really the function has a different value, right? So that sounds weird assumption or condition, right? But look at that example here. Here you have a nice nonlinear functions, right? So y depends on x in that way, exponential function, no problem. Here are 3 parameters, so what's the problem? Okay? But you see that if you do the following, if you just multiply out what that is, so f, x, beta, that is if you apply multiplication, then you see that beta 1 times e beta 2 times e beta 3x. Okay? This is just x to the power of e plus e is x e times x e. Okay? So if you now look at that functional form, you see what you actually have here is you have a constant times something that depends on x. Okay? So this is what you can estimate. What you would estimate is a constant and something that depends on x. The beta 3 is obviously identified, right? Because it varies with x. But now look at this here. You have just a constant, c. This is what you can estimate. But what is obvious from the formula is that there are a lot of various combinations, beta 1 and beta 2, that gives you exactly the same C. Right? And this is exactly what log identification means. Whatever X you use, right? It's not possible to distinguish between two combinations of beta 1 and beta 2 that gives you the same value of beta 1 times E beta 2. Right? See this? I think that's obvious, right? There's only one thing you can estimate, it's just a constant, but there are two parameters. So two parameters, one parameter you can estimate, often not identified. Yeah? That means with identification. And this is, in fact, something we already somehow experienced in the linear model also. In the linear model, that would mean that all the parameters here of our regressor matrix X are identified if the regressor matrix has full rank. Right? Remember that when we talk about that assumption here that the regressor matrix has full rank, my default example was just suppose for whatever reason you type in 2 times exactly the same regressor matrix, the same variable, right? So you type in regressor and whatever reason the CP, right? You type in the same regressor twice, right? And so on. So then you have a regressor matrix with 2 identical columns, obviously not full rank. And the square estimator says, I'm sorry, the matrix X prime X does not exist, it's not invertible, right? I cannot solve. Right? Well, this is exactly what happens here, right? Then, if you have 2 times exactly the same regressor, then you can have a lot of combinations of betas, right, for the exactly the same regressor, which gives you exactly the same Y. Yeah? So this is something, this identification issue is, as you can see here, more hidden, not so obvious in the nonlinear framework, but it's also there, however, in a much more obvious way in the linear regression framework. Yeah? All right. So, what about the statistical properties of nonlinear square estimation? So, this is something here which will be biased in small samples, but it's consistent. Right? So if I have a lot of observations, I'm fine with nonlinear square. Look at the covariance matrix of that vector of unknown parameters that we estimate with non-linear least squares. The covariance matrix here can be approximated like this. Yeah, look here, the formula looks exactly like the covariance matrix. Like the covariance matrix in the linear regression model, but the parameters have, of course, different meanings, right? So look here. The S square is in fact nothing but the sum of squared residuals, right? So this is really a one-to-one generalization, very easy, right? So if f would be a linear function, if we would be back in the linear regression model, then that would be just the 1 over n minus k sum of ui squared, the sum of square residuals, right? And remember that here, because we divided by n minus k, we could show that it's really an unbiased estimate of the variance of the residuals. Right. So that's s squared, and this here has to be reinterpreted now. It looks exactly like in the formula for the linear model, but of course now we have no linear f anymore, and this is what x is now. And here you need a little bit, this is a very sloppy, a little bit sloppy notation, because x is an n times k matrix. We have k parameters we want to estimate, right? And n observations. Then we have n times k matrix. So this looks like a vector, right? But it's actually because, look here, this is a partial derivative with respect to a vector, right? To a k-dimensional vector. And therefore, this is actually here something, this is an n times k matrix. Yeah, so this is here, you can say this is partial derivative with respect to f, with exactly? Well, if f would be a linear function, then this would be just our regressor matrix. Yeah? So, does it make sense? Okay? So look, if you remember here the linear regression model, we talked a lot about how that formula makes sense in the context of the regressor model. We talked about that, well, if we have a higher variance in the axis, right, that's good for our variance of the estimator, because then we have more information about x, and that drives the variance of the estimators down. Okay? And we saw, well, the higher the correlation between these regressors in the linear regression model, the higher the matrix, the higher the variance of the in here in the corresponding matrix. Because if we have multicollinearity between regressors, so if one regressor is very similar to the others, the least square estimator has problems to distinguish where comes the impact from. From that regressors, beta 1, or from the other one, beta 2, which is so closely related to the first one. Right? So the more independent, the more uncorrelated my regressors in the linear regression models are, the better. Because then it's really easy to distinguish where comes the impact from. And I can easily estimate beta 1, beta 2, beta 3, and so on. And that results in a small variance covariance matrix and efficient estimates. Yeah? If it's the other way around, then you have a multicollinearity problem, right? And it's hard to distinguish. This is exactly the fact, you know, where all t-tests may say, I'm not sure whether this regressor is significant, right? So you might have 5 t-tests that all say, I'm not sure, it could be 0, right? For each one. But if you ask the f-test, come on, are all of them 0? Then the f-test is pretty sure, no. Reject, right? At least one of those is significant. I just don't know which of them. Okay? This is the multicollinearity problem. And this explains to you here why standard errors are getting big if you have a multicollinearity problem. And now let us look how does that multicollinearity problem translates into a nonlinear framework. Okay? So look, when are, in the first row here, first column, there are the partial derivatives of my function, my given data vector, with respect to beta 1, first coefficient. In the second one, it's with respect to beta 2. Right? And now suppose we are exactly in that collinearity problem thing, that the first and the second column are very similar. Right? So these derivatives, the value of these derivatives, are very similar to the value of these derivatives. What does it mean? It means, in fact, exactly the same as in the linear regression model. It means that if I increase beta 1 a little bit, then I have some changes in f. Right? Corresponding here to the partial derivatives. F changes a little bit if I change beta 1 a little bit. But if I change beta 2 a little bit instead, exactly the same results. Right? Because I just said, let's look at the case where the first all derivatives with respect to beta 1, first column of x, are more or less exactly the same as in the second column, where I look at the derivatives with respect to beta 2. So, if these two vectors of first derivatives are more or less identical, that means that I cannot distinguish between beta 1 and beta 2. This is exactly the same intuition, exactly the same reason why it makes sense to talk about the covariance matrix of here my nonlinear square estimator based on these first derivatives. Okay? And this is why, of course, you know, it's a generalization of the variance covariance estimator of the linear model. All right? So the more different the response of my function f with respect to the different betas is, the more easier is it for me to distinguish between the betas and to estimate them. Right? Same intuition. Very natural assumption. Okay, here some a summary of the asymptotic property. Yeah, I already told you that in small samples, you know, it might be a problem, but if you have a decent large sample, then one can show that, well, look here, standard assumptions is all normally distributed asymptotically, right? So if it's normal, these are of course the final sample approximation then, so that's the true value, and this is my covariance estimate, covariance matrix I estimated. Okay. In fact, one can show that these nonlinear least square estimator is at least asymptotically efficient. Remember, the least square estimator under standard assumption was efficient, bam. Efficient in the class of linear unbiased estimators. Right? It wasn't one of those variances. Right? That was Gauss Mark. Here we can only say it's asymptotically efficient. So if you go n for to infinity, if you have a large sample, then you can say, well, it's not possible to have a better estimator than that one. If you don't have a consistent asymptotically unbiased. Okay. The asymptotic normality here is, of course, that's very important as well, because it allows you to apply it standard. Remember last chapter, right? We called the T and the F tests, and all these are based on the assumption that something is normally distributed, right? So if it's not normally distributed, then you can apply T and F tests. Yeah? And bootstrapping is here. All right. So good news, right? So we see it's a small, it's not a very long chapter about nonlinear regression, because you know most of the things just generalize to that case if I know the function for. Oops. So now let's talk about some, because that's new, about some numerical aspects, right? So this is really something different, right? If you estimate it with a computer program, as I already said, the square estimation has a closed form solution, so it's just solving an equation. But nonlinear square estimation, you know, you have to iterate, you know, it's not possible to solve for the beta analytically and write down the nonlinear square estimator. You just have to, what you can do is write down the first order conditions, right, that depend on the unknown parameters, and then solve numerically. So, and here's a notation to explain how these numerical maximizers or optimizers that are implemented in modern software work in principle, right? So look here, suppose you have theta is now a vector of unknown parameters, you know that notation already from our general remarks about statistical tests. So, and f is the objective function. So this is the function that you want to minimize, right? Like the sum of squared residuals, if you have nonlinear least square regressions, then you want to minimize the sum of squared residuals, right? So this is a function that depends on the vector of unknown parameters, of course, that you want to minimize. So let's go back. That would be our f. F would be s, and beta would be theta, right? So that's a special case of this here. Okay. Okay, all right. We have a function f. Right? You have to decide which function you want. Maybe you want to minimize the square, maybe some more general function. Well, let's see what's happening in the next chapters, right? When we go beyond these squares. So next thing you want to do is, well, we have a multivariate function. You want to optimize, maximize, minimize, whatever. Right? You know what to do, yeah? Take first order conditions. So take the partial derivatives. We have a gradient vector, it's called the gradient vector, gradient. So the vector of first order partial derivatives for all the, so if this is a k-dimensional vector, we have k parameters in this vector, we want to estimate them, we have k partial derivatives. And there should be all zero if it's a stationary point, right? So exactly what we do here. So this would be, oops, where is it? Here, this is now G, right? G for gradient. So, but that's not enough because we know, well, if we want to talk about minimization, maximization, you remember math, right? Then first order conditions are often not enough, right? There's strange thing going on, local versus global, maximization, settle points, right? Have first orders, have all the first order conditions fulfilled, but have still no minimum and maximum, so that's a settle point, right? So, second order derivatives play a role in multivariate optimization, and all the second order derivatives are summarized in so-called Hessian matrix, Hessian in German, right? This is just the matrix of all the second order derivatives. The pure ones are diagonal, and the mixed ones are the off diagonal, right? If the function f is a nice one, so not a drastic strange one, then all these mixed derivatives of second order do not depend on the order of differentiation. In other words, Hessian matrices are typically symmetric matrices, right? So we need this one. We know that the optimum values are characterized by the fourth order condition. So when the gradient is 0, that's the necessary condition. Yeah, and this is how typically those numerical optimization procedures that are implemented in all modern software go on. All of them need some initial estimates. They need a starting point. All these programs allow you to tell the program what's your starting point. If you don't know the starting point, the program typically starts with a naive estimate. Some start always with putting everything to 0, right? Some start with some naive estimation, mean square or something like that, right? But you need a starting point, okay? So you need a first guess, beta 0, initial point. And then there's algorithm that tries to improve the value of f. So you can now calculate f of theta 0, yeah, of course. And then you ask, well, maybe I can do better. And of course, it should be better, right? Just getting an initial value that this is always guess value is already the optimal one that would be really low, right? So, and now the question is, and these are the details of the numerical algorithm, how the algorithm finds a little bit of better value. Right? You try it out and have it, and if you find a little bit better value, then you have the next step. And then it evaluates this one, and it goes further and further and further, and iterates. And the idea that if it's a good algorithm, well, look, then it should converge to some optimal value. But the issue is, and that's now different to least square estimation. Well, in all these numerical algorithms, there is somewhere determined the stopping rule, right? So usually the stopping rule is, you can do it in two ways. You can define the stopping rule with respect to the thetas. So you can say if the thetas do not change from iteration to iteration more than your decision, right? Or the program's decision, if you don't know, right? Then there are some given values, right? Dan's values. So you can define it based on the thetas. So if the thetas remain constant or just change in the 10th decimal point or something like that, you don't care, you stop, right? Otherwise, it goes forever and ever, the algorithm doesn't want to have a result, right? That's one way. Or you define it with respect to f. your goal function. You say if the goal function does not improve more than from step n to n plus 1, then I stop. Okay? So depending on the stopping rule, right? And again, you know, if you go into the detail of R or whatever program you use, you know, you can tell the program what's your stopping rule, you know, and how generous you are, or how impatient, or how patient, right? And then the program tells you, well, I stopped after 17 or 150 or whatever iterations, right? And of course, somehow, you know, the number of iterations the program takes until it stops depends, of course, on the quality of your initial value, right? If your initial estimate, the starting point, you just guess, right, is close to the optimal value, yeah, well, then the iteration stops easy, right? If it's far away, then it might take some time, right? So that's one thing, and of course, it's never a good sign when this algorithm takes a long time, takes a lot of iterations, because that means that the improvements are small, you know, and that maybe the optimum is not so well defined. Okay, so these, before I show you or remind you at some classic numerical example in the numerical process how that is done, let's talk a little bit about the problems that may happen. So first of all, and this is related to the question of choosing a good initial point, you know, suppose this is your f, right? And here is theta, and here is f is theta, and you're looking for, let's suppose you're looking for the minimum of the sum of squares, you're looking for some optimum, right? So, and you see already what might happen numerically. It can be that if your starting point is here, then it converges to that one. And that the computer tells you, found the optimum, no, it's not better here to be here, because it always looks in this direction, but it does not go from here to there. So this global optimum, which you are where you're actually after, is just ignored by the program. It's not found, it's overlooked. Okay? So, what's the implication of that? How to circumvent that problem? Or say ameliorate it in practice. Yeah?
Maybe do multiple trials and
multiple trials with what?
with the initial estimate.
Yeah. Yeah, obviously, right? Very straightforward idea. Great. Yeah. If this is a problem, if the initial estimate is a problem, well then try out some other ones. Right? And if your numerical optimization gives you converges always with the same value, yeah, then you can be pretty sure. Okay? Or if you try another one, right? Suppose you're here, yeah, and actually you converge to global, but you're not sure, right? Maybe you are not here, but remember there. Yeah, well then try another initial estimate, and then it might converge to another optimum, and then you just compare the values, and then you know what the global optimum is. Okay. So this is something that can happen, right? So in particular, if you come on, you're economist, so you have some priors about plausible values, so right. Especially if you think, oh, these are strange values. I would have expected this and that. Yeah, maybe you would give you some sensitivity analysis of your estimation with respect to the initial values. Okay. Global, local versus global. So now, identification problem. It pops up also in the nonlinear numerical estimation thing. What does that mean? Well, let me another picture here. You can see that, by the way. Okay, so again, the task is to maximize f connected to the least squared or something like that, some goal function, and your goal function actually looks like this. Ooh, you see, right, what's going on. There is a maximum here. I don't know, is it here or is it there? You see already. No problem. If you have, for whatever reason, yeah, I don't know, not for whatever reason, yeah, it's clear what's going on. This problem here means I change the parameter vector, the unknown parameter vector, rather drastically, but the effect on my goal function is super weak. There is some effect, yes, but come on, it's hard to deal, right? So this is related to the identification problem we talked before, because this means that my model has problems to distinguish the response of my endogenous variables to very different values of my unknown parameter vector. Right? It's like the multicollinearity problem. Right? Two very different parameter vectors give very similar results for y. Same here. Right? So here you see that it's really hard, right, to find the optimum and we already saw, right, because we talked about the covariance matrix. If you have a problem like this, which you solve this with nonlinear least square or some numerical optimization problem, yeah, you might find that. But for sure, the standard errors that are reported will be huge, right? Because it's just not clear whether it's really here or maybe there. Okay? Because the first derivative is close to 0. All the time. Not only for that one, but only for values that are very different. Okay, so these are numerical problems, right? This is a numerical problem if your goal function is not well behaved, so it's not always all over convex, concave or convex, right? You have local and global optimum, something like that. And this here is something, well, if your data, is highly correlated, for example, and so that you have problems to identify the parameters. This would lead to something like this. All right. So Gauss-Newton method. I guess I learned that already in school. Well, I saw that in school, right? I teach this somehow in the first semester in math, I believe. So, but this is something the computer does, right? So, this is here the Gauss-Newton method. You might already know here from a picture like that. I've written down in the notation we have here just for f and g and h, so for in the multi-dimensional thing, right? So what's actually going on with the computer? Look, here we have here the first order. We have here the vector of first order derivatives, which we want to have to be 0 because this is the first order condition that the first order derivatives are all 0, right? So we're looking for zeros of that function, or roots, so to say. So this is the linearization, and we see that this is this is more or less a multivariate generalization of a tangent, right? So you have a nonlinear function, and you want to linearize it locally. You can do that in 2 dimensions with a tangent, right? At that point, in a multivariate setting, it's like that here. You have first, if you want to, so here is how you go from step h to h plus 1, right? Because this is all you have to know, right? If you have a starting point and you know the rule
then you also know how to go from theta 1 to theta 2, theta 2 to theta 3, and so on and so on and so on. Okay? And at every step, you evaluate your, you look whether your stopping rule tells you it's enough, and if not, you go further. Okay? So here's the stopping rule, so to say. Here's how you go from step h to step h plus 1. So, you linearize this nonlinear function here locally at that point, at that vector. This is what you know because you're already in step h, right? Or in step 0 if you want, right? So that's the value of the function. And here, this is the Hessian matrix. Because in the tangent, right, it's the first derivative of the function. Now the function is the first derivative. So the first derivative of the first derivative is the second derivative. Okay? So this here is again, exactly, this has exactly the same form as a tangent if you would assume that this is a univariate function. Yeah. Okay, and now we know that if that would be an optimum, then the first order derivatives are all 0. So you put in 0 here on the left-hand side, and you solve now for theta, because this is then your optimum, right? And if you do that, this is the equation you get. So that would be the way your computer proceeds when you apply the Gauss-Newton method in order to find numerically the roots of a nonlinear function. Okay. What you can show, now we would have to invest much more math, is that this here, under some regularity conditions, G and H, these iterations actually converge to a local optimum. But yeah, it only local, right? Because each local optimum, minimum or maximum, whatever, has that all the first order derivatives are 0, right? If it's a global maximum, well, that depends on the function, whether it's overly concave, overly convex, or if we just have to check here with some sensitivity analysis with respect to initial value, whether we have really a global optimum or not, or only some uninteresting local optimum. Okay, so if you rewrite this for univariate functions, you get here the tangent, and you're back to that figure here. Right? So this here we write down it for the very special case that theta is just one parameter, and g of theta is now the function where we're looking for the roots. And this is now the first derivative, right? Because first derivative 0, this gives us a stationary point. So this is how these g function, the first order function, actually would look like. I don't know it, but this is just for demonstration, right? This is my starting point, my initial guess, and I see, oh no, I'm sorry. It's not 0. So, not surprisingly, my first guess, my initial estimate, my naive assumption about theta is not confirmed by the data. The first derivatives are not fulfilled, so I can do better than that. And this is how that here works. The Gauss-Newton now tells me, okay, you know what? Take the first derivative of that function here locally, and then replace this strange nonlinear function g, I have no idea how it looks like, with a linear approximation to the tangent. And check what is the root of the tangent. And this is that one. And this gives you exactly the next step. Right? So, and now you evaluate it again and see, oh no, it's still not 0, right? But if the process converges, the value should be closer to 0, like here. And then you do the same thing, because it's an algorithm, you always do the same thing again and again and again. For theta 1, the tangent here is like this, the root of the tangent is here, and you see this is neither. Yeah? This figure here strongly suggests that if you now go there, that the tangent will be even closer to the optimum, and so on and so on. Right? And the stopping rule is now, well, when it's defined with respect to the theta, if this change here is getting smaller and smaller and smaller, and maybe if it's small enough, then I say, come on, that's fine. I think I'm close to the optimum. Or you define it with respect to the growth function here, and say, okay, then this is here 0.0, blah, 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 it's okay. Yeah. Okay. This is how the Newton, this is what you computed as. What are the data you all the programs when you apply not only nonlinear squares, but whenever you maximize or minimize the nonlinear function. Okay, always iterate the process with some numerical problem. Okay? Right. Enough nonlinearity. Back to linear. Okay, but it's the generalized least square model now we're talking about, and this is here you see what we do, and I think most of you should know from the bachelor what the GNS is, what increment variables are, and maybe also what GMM. I'm not sure. That's not at least not in the bachelor program at Gefei-FIONA. Math and likelihood, sometimes yes, sometimes no. This definitely not. So that's the plan for the rest of the semester, right? I guess I organized it a little bit asymmetrically. I guess that that part 2 ends here, and then there are only 2 slides left for part 3. Okay? So I think we are good in time, right? To cover. This is and like this. So we're still talking about the slope of a regression line, right? So in the 2-dimensional case. So recall the so-called standard or traditional or classical assumption of the linear regression model, right? This is already known. Yeah. Usually this a slide like this appears at the very beginning of a standard econometrics textbook, right? So we know the functional form, right? Especially here we look at linear models. Here are some regularity conditions about x, right? Remember what that means. That means that this f prime x, even if n goes to infinity, and x prime x is a k times k matrix that consists, however, where each entry is, however, a product of n sums, and so there is, it can explode or it can go to 0, right? We have this example, but here's the assumption, no, come on. We don't do that in extreme cases. Well, we have a well-behaved limit, and therefore we are sure that under some assumptions, our estimate behaves well, even if n goes to infinity. Now, this was the assumption we needed in order to show that the least square estimator is a consistent estimator. Yeah? Okay. So that was the assumption about x. Yeah, and of course, regularity also meant then, of course, that we have no perfect collinearity through rank and all these things. And you remember. And then we talked a lot about the errors. And their relation to the regressors in particular. So a lot of the standard econometric results, especially in the bachelor here, are derived from the assumption of strict heterogeneity. Special case, non-random regressors, where strict heterogeneity is, so to say, by assumption, right? And remember that was a very strong assumption because it implies that the errors are uncorrelated with, or that the regressors are uncorrelated with not only with the current error of the same time period or for the same person, but with all others, right? And especially if I have a time series model, then that was super unrealistic. It was more or less by construction, not strictly exogenous. If I have a lag endogenous variable on the right-hand side, if y depends on y minus 1, if today depends on yesterday, then of course, yesterday has some, say, only if it's a strict extra. If we assume this in some applications unrealistic assumptions about strict exogeneity. Fortunately, we could show that if we go to a weaker exogeneity concept that can include also time series applications where we have lag endogenous variables, then the assumption here, then we can derive consistent and asymptotically unbiased estimates even for lag endogenous variables, and the assumption there was that we have no articulation of the errors. That was important here. Another assumption we used in particular for the Gauss-Markov proof, and also for dividing standard errors and so on, we need the assumptions about covariance matrix so that we have no heteroscedasticity of the errors, meaning that the covariance matrix of the errors was just sigma squared times the identity matrix. So here is omega jj with j's that are elements. This is just sigma squared for all j's. Alright? And well, the distribution was always known. So for example, we assume that it's normally distributed, but again that wasn't so important, right? We show that if n goes to infinity, then we don't have to make normality assumption about u. We only need to know that there's some independence, so they're not perfectly correlated and all things like that. Okay, so this is a framework, and that would be in your mind, what assumptions do I need for this result, what assumptions do I need for that result, right? To be, not confused. Okay. Now, as I said, here a little bit more detail what we do about the next chapters. So this is the rest of part 2 of the lecture. So first we talk about generalized least squares and related topics, because generalized least square means, well, how to generalize the least square estimator if some of the assumptions do not hold. And the assumptions we talk here about in particular, first we talk about autocorrelation and heteroscedastic errors, right? That we know already from bachelor. Then a very important thing is endogeneity of regressors, right? We saw that already, but if the heterogeneity assumption was not fulfilled, then the square estimation broke down, right? Was infeasible, led to inconsistent estimates, right? So we'll see that this here is more or less of, well, let's say of second order importance, right? You will see in a minute why I say that. This is here of first order importance, because it really means, come on, yeah, here you have less efficient, not so nice, yeah, but still it's okay, and here, no, don't. Wrong. Okay. Here's some ways to deal with heterogeneity and autocorrelation. So this is a very, here in 9 and 10, we talk about the two other dominant statistical estimation concepts in econometrics, in addition to least square estimation, or generalized least square estimation, whatever, non-linear, it's GMM and it's maximum likelihood. Okay, so we'll talk a little bit about that one, about those two and how they are related properly to least squares. And then we talk about penalized least square estimation. So this is more reason, I would say, especially in economics, somehow building the bridge to achieve that. Yeah. Okay, so generalized least square, let's start with some overview slides, right? So we're still in the linear regression model. But now, look, this view, now we say, yeah, maybe the covariance matrix of the use is not just the diagonal matrix. Maybe it's some omega, some matrix. Okay, it's a covariance matrix, so we know it's symmetric. We know, what else do we know about the covariance matrix? Symmetric and? Typical example. Not anymore. Yeah?
Positive indefinite.
Yeah, exactly. Positive definite, right? Because on the diagonal, remember, on the diagonal, there are variances, and the variance should be positive, right? So at least they cannot be negative not, we discussed that positive diagonal elements are a necessary condition, but not sufficient for semi-definiteness of a matrix, right? You had this, I saw it on Blackboard that Leah discussed with you the slides on eigenvalues and positive definiteness, right? So there are easy examples to see where you have positive diagonals and still, because some eigenvalues are negative, no positive definiteness, but this is what we know, what we just assume if we assume that this is a covariant matrix. Yeah? In fact, if you estimate covariance matrix in complicated models, right? The main task is to find or to assure that your estimator gives you a positive definite covariance matrix. Right? This is very often in footnotes, right? That this is a nice algorithm, but we believe that covariance matrix, which we estimated, is not positive definite. Well, right? And cannot be interpreted covariantly, then it's not. Right? Alright, so here we assume it's a covariance matrix, and that of course, here's an overview of some main results we derive now. So if this is not, if you are not in the classical case, here omega is not just an matrix, then we will show that the generalized square estimator we now devise is an efficient estimation. So it generalizes the Gauss-Markov result if we have autocollated or heteroscedastic errors. Right? So in a very general case of omega. Right? So this is now not the same anymore. Omega may depend on the axis, right? However, if you just if you're not sure how to do it, or if you don't know that, if you're just naive, or you only have natural and you don't know about generalized square, you don't know least square, for whatever reason, you ignore that. And this is why I said that these are more or less second order problems we're now talking about. So just if you wrongly apply GLS, you will see that if you wrongly ignore GLS and just apply naively least square, although omega is not a nominal, your estimate will still be unbiased. Right? Of course, know that while you regressors then, right? So if you have a lot of observations, right, then maybe the gain of having GLS instead of least square is for your estimation not so big. But let's see. Here is a slide that shows you in the context of time series, I would say, the relevance or how to detect or what is meant with autocorrelation and heteroscedasticity in the data. Right? Look here, this figure here, this should be, I guess it's a simulated data, right? But let's assume that this is your time periods. Okay, this was simplicity. So that there's a natural ordering here on the axis. Not just I have 200 persons and I don't know how to group them, right? Then there's no natural ordering, right? But if I have time, then it's a natural ordering. And it makes sense to put, so then every researcher that would try to plot the data would do it in exactly the same way, because no one would just throw the time periods all around or something like that, right? Okay. So here you see a time series where obviously the variance has changed over time, right? Here the fluctuations are obviously smaller than there. Here crisis period, I don't know, here calm period. Those who are interested in macro know that until the financial crisis in 2007, there was a period of about, 20 years or so, macroeconomics were very happy. They thought they understood everything, right? And there was the time of very low fluctuations in major macroeconomic variables. It's called the Great Moderation, right? Of course, you know the Great Recession, right? That was a great moderation. And some macro guys were really so bold to say, this is because of us. Because we understood taught people and politicians how to do macro, right? Central banks are independent, they know what they do, blah, 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 blah. Okay, then comes the financial crisis. Yeah, well, and now variance was a little bit higher than that. And then comes Corona. And, okay, so macroeconomics is still an active research field. Not all problems are solved, as some people thought in the early 2000s. Okay, changes in the variances are in a time series context. All right, this is easy to see, right? And it's also easy to see if you work with high frequent data. So if you're doing financial econometrics, or if you look at stock prices, or exchange rates, or something like that, then you will see from the plot of the time series, there are calm periods, and then, whoa, what's going on here? New information in the market, blah, 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 and then it goes down again, right? So if you work with financial market data, then heteroscedasticity is not only like this, you have 10 years calm, 10 years crisis, it's going within the day, probably. It's a high volatility period, and low volatility, and so on, right? So homoscedasticity assumption in financial market data, right? In macroeconomic time series data, it's also there, right? But it's not so easy to see. A few years ago, Rob Engel got the Nobel Prize in economics, and he introduced into the literature the so-called arch models. You've heard of that? If not, great. Come next to the time series analysis next semester. An arch model is a model that tries to replicate the empirical pattern that if volatility is high today, it tends to be high tomorrow. Right? So there's an arch means autoregressive conditional heteroscedasticity. So it's autoregressive, meaning today depends on yesterday, right? So, and this is exactly what's going on very often in financial market data. So that you have periods of high volatility, and it's not just sigma squared, right? So high volatility today, tomorrow, I don't know, sigma squared, no. If you have high volatility today, then you have high volatility tomorrow. Not deterministic, but it tends to be. There's a higher probability to have high volatility than the other way around, right? And these arch model here the variance look more like this, right? So you have something like that, and something like that, and something like that. So we have these periods of, you have something people call volatility clustering, right? So the periods of high volatility are not just randomly distributed all over the place, but they're clustered in certain periods. Okay. So, this is heteroscedasticity. So in time series analysis, it has some saying, right? But it's much more pure and critical, I would say, and much more discussed also in cross-section data, right? So if you're doing microeconometrics maybe next semester, or if you apply this microeconometrics, your econometrics to microeconometric data, like survey data or something like that, right? Step data or whatever, right? Then there's not much to say about autocorrelation, right? Because often you have just a cross-section and it makes no sense to talk about autocorrelation because today, yesterday, there's no yesterday, just a cross-section, right? Where I have a panel and I have only 5 survey waves. And then also it makes not much sense to talk about correlation because I have only 5 periods, come on, right? So it still makes it interesting, to follow the people along time, right? But correlation over time is much less critical in those applications than heteroscedasticity. Right? So heteroscedasticity in cross-sectional data, my bachelor example, and that is, did anyone here econometrics in bachelor here with me? 1, 2, 3, don't be shy. 4, 5, yay. Okay, this is a food expenditure example. In the textbook I use in the bachelor, the leading example in the first chapters is a cross-section of some households, and the question is, how are their food expenditure related to their income? And then we have a scatter plot, right? And then what you see is that the scatter plot goes like this. Not like that, but like this. And that means that there's more variation in the food expenditure for high-income people than for low-income people. It's a higher variance, higher variance for high-income people than for low. And the idea is, the intuition is, yeah, well, if you're poor, then you always spend all your money for food. Well, you have no choice, right? So there's not much variation, yeah, spend everything. But if you're very rich, then there might be months, you know, where you spend a lot for food because you can afford it, right? And in some periods you just go to Aldi like anyone else. No party, no extra party, right? So, a lot of fluctuations, right? And this is exactly what happens with step data and survey data and whatever. For some reasons, you know, people behave very, there's a lot of uncertainty. And the uncertainty, hopefully you find the source of that uncertainty, so you can model it, you can talk about it, right? But this is the issue in cross-section. All right, so let's talk about the effects of these two things. We begin with heteroscedasticity. Right, this is technically what heteroscedasticity means. Right, we have here a linear regression model, right? X and Y, so this is a simple linear regression. We have only one regressor, this is Y, and this is the probability of observing Y, or not exactly probability, it's the value of the density function, of observing Y given X. And what we do is we do linear regression, then we just here look at the expected value. Yeah, and this would be the regression line. So we have three different realizations of X, right? And what we say is, well, yeah, this is my regression line, and here's a distribution around that, right? So, because we're not 100% sure that the value of Y given X is there, we only can estimate it, so we have some standard errors around and so on. And what you see here is, this is a case of heteroscedasticity, the uncertainty around some points depend on X, right? So in the classical linear regression model, under homoscedastic errors, there is only one standard error. And the standard error is the same for all X's all around the place, right? The width of the standard errors of the confidence bands is always the same. Well, rich people, poor people, I'm always, the level of uncertainty, the uncertainty is always the same. Here, this figure shows you that for a small x, exactly that this fits nicely to my expenditure thing, right? So for small x's, low income, you make a prediction for food expenditure, and your uncertainty around that prediction is very small. So you have steep density function, right? So it's somewhere here, you know, it's probably there, but not there. Come on, right? Here, high income, same prediction, so linear function, fine. But look here, for high income people, a lot of uncertainty. It's not only variable up here, you know, even there, it could be there, but it could be there, right? So much more uncertainty. Okay. So the variance depend on X. This is something which violates, of course, the homoscedasticity assumption of the classical model. Okay. So now let's talk about, so how important is that observation? Right? So what if we just ignore that? If we, for whatever reason, just blindly use ordinary square, so we assume that the covariance matrix of the use is diagonal, we assume that our classical thing is okay, although in reality it's not. but we overlooked this, right? So, this is what we do here. This is the least square estimator, the ordinary least square estimator, right? You know that formula. Okay. And if you look at the proof, into the proof of unbiasedness, you see that the only assumption we actually need there was that X is exogenous, and the errors are expected value 0. In the proof of the unbiasedness of the least square estimator in the linear regression model, we didn't make use of the assumption that the errors are homoscedastic or the errors have no autocorrelation. It doesn't show up in the proof, we don't use it. And therefore, that's the beauty of these mathematical proofs. They also show us what assumptions we actually need to prove the result, and if we don't need an assumption, then obviously it also works if that assumption does not hold, because we don't need it. And this is why ordinary square estimators are still unbiased when least square. Well, when the as long as the regressors are exogenous. Okay, and this is why you might say, oh, come on, I'm only interested in point estimates. I want to have an estimate. And I have no clue what that means, standard error, estimation uncertainty, then okay, right. It makes not much sense to say I don't care about estimation uncertainty, but if you just want a point estimate, then it doesn't matter a lot. Okay? I ignore heteroscedasticity, I ignore autocorrelation. As long as I have exogenous regressors, it doesn't matter a lot. Especially if I have a lot of observations. Alright. But what about the variance? And then it's somehow obvious, right? So that might be a big problem. Because if we look at the derivation of the ordinary least square variance estimator of my ordinary least square estimator, so then I would estimate, if I apply the ordinary square estimator to my model, because I ignore the fact that the covariance matrix of the U's is not diagonal but omega, then I would say, this is my least square variance. But if you just apply matrix algebra and with 1, 2, 3 rules, how the covariance matrix responds to a matrix product, I think Leah will do that in the next tutorial also to revise this, right? It's easy to see that the covariance matrix of given X in the general case of omega here, so this is omega now, looks like this. And of course, because it's a generalization of the ordinary square estimator, in the special case that omega is just a diagonal matrix, if you plug that in, then everything cancels out and you're back to that. Okay? Just do this, because you have to a little bit, you have to be able to deal with matrix simplification. Alright, so look, whoa, this looks complicated, right? And this is obviously, if omega is not diagonal, then that's just a different matrix than this one. Right? So what? Well, all our tests, T and F tests, that were based on that matrix are now just wrong. Right? If we apply this covariance matrix of our estimator to do here our T and F test and whatever test we want to do, but in fact the covariance matrix looks like this, then we're using the wrong covariance matrix for our tests, and then of course test results are just misleading. They're just not valid, wrong. This is what I meant with first order and second order problem, right? So you have a first order problem in the second moments, right? Okay. So, and of course what you can also see, right, because we are talking about the estimation, if you go to the Gauss-Markov proof, again, you see immediately, oops, here we plug in that the covariance matrix is sigma squared times identity. If we can't do this, then no proof, right? So obviously, if we apply ordinary least square, although the assumptions do not hold, then we cannot prove the Gauss-Markov, then ordinary square is no longer efficient. Right? It's still unbiased, okay. So on average, no systematic mistake, blah, blah, blah. But it's not longer efficient. We can do better, right? Somehow. And more critically, all the tests here go down. All right. So OLS remains consistent, right? So this bias goes away if n goes to infinity, and it's all asymptotically normal. That's all fine. But the standard errors are wrong. And of course, you know, if x contains less y, then it's not exhaustion anymore, and then it's not unbiased, and then everything goes down. Okay, so takeaway, major takeaway. If we apply ordinary squares, and now you see why it's, I guess at the beginning I just talked about least squares, right? Now it makes sense to be more precise. The least squares in the first chapters is what people say is the ordinary least squares, to make a difference to the generalized least square we now talk about. Okay, so the major takeaway is if you're just interested in the point estimation, then yeah, you might say it's fine for me. I have not the efficient estimate, but come on, it's still consistent, right? But if you want to make tests, and come on, you always want to make tests, right? Then applying OLS in the GLS framework is not good. All right, so there are two strategies to account for that. Now, if you don't want to be the stupid guy that applies ordinary square, although he should apply something else, right? What can you do? There are two options. The first option is what we took here, is that you adjust the ordinary square estimator, and we will introduce and look how you adjust it. You adjust it in a way such that the adjusted estimator fulfills again the classical assumptions where you know that you have an efficient estimate. This adjustment, I will show you in a second, this will be the generalized least square estimator. So this is one way. This is, so to say, the best way, right? Because then you repair all the problems, right? Then you have back to the correct standard error. If you have an efficient estimator, this is the best thing you can do. Okay, but you know, when you're an economist, you know, best you can do, there's always a trade-off. Always a trade-off, right? You can do this under some assumption, right? We will talk about these assumptions. If you don't want to make these assumptions, if you're not able to do it, or whatever, then there's a second alternative, and this is very often done. People say, I have so much observations, I don't care about efficiency. I think I have a consistent estimator. And actually, GLS, strange concept. Problems in practice. Don't know how to do that. So, one opportunity is, well, if there is something like robust standard errors, so standard errors that are not just the naive ordinary square standard errors, which are wrong, but if I'm able to somehow correct the standard errors so that they are still valid, although I have heteroscedastic order-coded errors, then I'm fine. Then I have an okay estimator for beta or theta or whatever, and I have correct standard errors. And this is all I want to have. Okay? If you look at empirical papers, you will see very often that footnote in the table. We use lower standard errors. I show you what kind of lower standard errors they use, right? This is
something, in a way, you know, especially time series econometricians like me, shrug when they see that, because it's just, you know, I don't care about everything, I just type in, hey computer, use robust standard errors, and then all my problems are somehow magically solved. This sounds too good to be true, and in many cases it is too good to be true, right? So, but this is how it's often done, right? From a time series econometrics process, you know, look, this here means, yeah, I see there might be some issues in autocorrelation and heteroscedasticity, but I don't care. What, you don't care? You're not interested in that fact? Look here, financial market data, crisis, non-crisis, breaks in volatility, autocorrelation. Oh, that's interesting for forecasting, no? You don't care? Yeah. If people don't care about the dynamics of their model, then they use robust errors or robust autocorrelation. If they don't care about the rules of heteroscedasticity, if they don't want to learn from the data, the rich people are what, and so on, then they use robust standard errors. Right? So this is why I think, yeah, robust standard errors is a solution, often used, but it's a I don't care solution. Maybe in your application, it makes sense to say something like that. Because actually you don't care, right? Yeah, because you have no dynamics in there, and autocorrelation is not interesting, and heteroscedasticity, whatever, you know, yeah, maybe. It depends on the application. Okay? So, if there is the possibility to care about, somehow to model the heteroscedasticity, right? We call the food expenditure example, but I understand the rich people, and then I can maybe, as you will see, it's relatively easy to modify the model, taking into account that heteroscedasticity in order to get a better estimate. You know, why should I not always do that? What could be the trade-off? My life as an economist is full of trade-offs. Okay? So, if I am convinced the root of heteroscedasticity is, for example, the level of income, I can modify it. And this is good. But what if this is wrong? What if it's not the income? It only looks like, in my small sample, like it would be the income. Yeah, you make an assumption, it could be wrong, and if it's wrong, then everything is wrong. Then you say, oh, I'm better than those guys using robust standard errors because I modeled the heteroscedasticity, I learned and then you learned the wrong thing, and then everything's wrong. Okay? So that's, you see, always a trade-off. Yeah? All right, so it's your decision in your application how important that is, whether it really is important in your application, and if you learn something from the data more, and if it's worth the risk. Just like that. Okay, so here is a slide which explains the generalizing square estimate, and it's really one slide. So, what is the idea? Look, here's the idea. Suppose you can, this phi here is a matrix that you multiply with your vector Q's. And now just suppose there is some phi matrix out there that you can use, forget it, of course always condition on the axis. When you multiply the U has these linear covariance matrices, right? Which is a problem. But now, if you multiply that U with phi, then the result is homoscedastic and free of population diagonal. Right? So, whoa, is that possible? Yes, it is. If you have some omega here, and you know it's positive nit, so you can always look at also at the
a non-singular positive definite matrix, then it's a mathematical result that you can always find a decomposition like this. And if you take the inverse of that, then whoop, it's like this. Okay? So if I knew omega, right? If I knew omega, I can always tell the computer, please give me this decomposition. Alright? And it has to do with the positive eigenvalues and the eigenvectors. This is what it calls that decomposition. Yeah? Okay. So, and now look what's going on. Now I multiply my whole model, so my model is y x beta plus u, and now I multiply from the left with that magic matrix here where all the eigenvectors are in and so on. Yeah? So, look, I can do that, why not? Right? If x is exogenous, then this is also exogenous, so no problem. And you see the tilde means now I have a linear regression model. Y tilde depends on x tilde times beta plus u tilde. Okay? Alright. This here shows you why we do this. Now we calculate the covariance matrix of that new linear regression model with the same beta, actually. Right? Look at the covariance matrix. The covariance matrix of u tilde is the covariance matrix of, this is u tilde, a construction. What's the covariance matrix of this times this? This is that covariance matrix of u times this. Yeah? We applied that rule already in the linear regression model. And now we just insert what we know about the covariance matrix of u. This is by assumption, just here, that one here. Omega, this is the covariance value of u. And now look what's going on. Jump, 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 jump. Oh. Identity matrix. Magic, right? So if we knew omega, it's always possible to find psi, if you know what eigenvalues are. And I'll decompose it. I do that. To modify my linear regression model just by pre-multiplying in order to obtain here residuals which just follow the classical assumption. So that means that if the residuals u tilde of this linear model here follow the classical assumption, that means, well, I can just apply ordinary least square to that model, to the tilde model, and I'm in the framework of Gauss-Markov. Everything is great. Efficient estimate, standard errors are correct. I'm back in chapter 2, or 3, or 4, I can't remember. Right? So all problems solved by pre-multiplying with this magic phi. So, and here you see what's happening with this is the OLS estimator for the tilde model. So this is x tilde prime, x tilde inverse, x tilde prime, y tilde. This is just the formula for the ordinary least square estimator of the tilde model. Right? See? Now I replace what x tilde is. X tilde is this, prime, x tilde minus 1 tilde. I just introduced what I know about x tilde and y tilde and so on. Now I have this, and if I now apply these 2 or 3 or 4 rules for matrix transposition and inversion and multiplication, right? You can generate, you can show, and I guess maybe Lea will do that in more detail if you're not sure. Yeah, look, you have here the transpose of a product, so just the other way around, right? And then you have the product of the inverse, so you can, again, the other way around. And if you do all this, if you apply all these matrix algebra rules, then everything cancels out and it looks like this. And this is the formula for the generalized least square. And the matrix And the main thing is that you understand that that this is really genius, right? You have a wonderful estimator, the ordinary square estimator, under some classical assumptions. Now the assumptions are violated. Oh, what can I do? I modify the model in a way that the classical model assumptions are met again. And then I apply the ordinary square estimator to the modified model, and this gives me the generalized square. And that, of course, depends on the detail. And of course, you see, if omega is a diagonal matrix, then, of course, it melts down to the ordinary square estimator. You cancel out this one. In a very similar way, it's easy to show how the covariance matrix of that generalized square estimator looks like. And you see, yeah, of course, omega plays a role. Right? And of course, if omega is diagonal, that formula melts down to the classical one, to sigma square x minus x. Alright? Well, that's GS. And here's again a reminder how to find the psi, right? I don't want to recall that because it's really explaining the slides. And yeah, the cholesterol composition of a positive spin matrix. You see, like, this is a mathematical thing here based on eigenvalues and eigenvectors. And if you find this here and you know it's positive definite, so these are all positive numbers, therefore you can get the square root of them because they're positive numbers, and this gives you this here, this. The starting point is that one here, and if d is a square because all positives, then you can rewrite it like this. And let me close, right? Let me just close here, here with that very similar example taken from the bachelor thing, right? Here, look. Here you have something like this, right? So you have a linear regression model, and the idea is, I have heteroscedasticity. The variance of my error depends on some variable vi, right? Maybe the income of someone, right? Maybe that's cross-section, and this is the income of the personality. And now you see how this modification, this Cholesky decomposition looks like in a very, very simple univariate examples. If you just divide now your equation by square root e, so the stars are the tildes of the other slide, right? So these are the tildes now. You divide the equation by square root e, then you have this tilde equation, and again you can show that if you now calculate the variance of this, you see immediately that the variance of that is just not because the dividing cancels out, it's just constant. Does not depend on anything more, and therefore you can read. And this shows you that in a way, the generalized least square estimator in heteroscedastic context is nothing but a weighted least square estimator. It weights those observations with high uncertainty down. Right? This is the intuition of why the generalized least square estimator is more efficient than the least square estimator. Because go back to that leading example with income and food expenditure, right? And suppose that rich people, high income, have higher variance, more fluctuations in their food expenditure. What does that mean? That means that the information content for the relation between income and food expenditure for poor people, information content is higher than for rich people. Because if I know that there is elasticity, then if I have a rich guy, I know a lot of uncertainty. So if I have an observation for that guy, I don't give so much weight, right? Because I know the information content of that is rather low, relatively low to a poor guy, where I know there's not much variation here. All right? So talking about heteroscedasticity translates in an estimation context in what is the information content of that observation. If there is high variance, that means low information content means in my calculation of an efficient estimator, it goes in with a lower weight than an observation with low uncertainty and high information. Okay? So, especially in the case of heteroscedasticity, the generalized least square estimator can be interpreted, also mathematically, as you see here, as a weighted least square estimator. The ordinary least square estimator weights each observation the same. Each observation has the same weight. Yeah, because sigma square is constant, right? So each observation has the same information content by assumption. Right? Look here, this was that here. Right? Here, this variable has higher information content than that. Yeah? Because here I know it fluctuates only a little bit around the true regression line, and here I know, come on, there might be a lot of variation here. So if I observe something like that, I don't take it too serious. Okay? If I observe here something like that, ooh, I have to take it serious. Okay, so GLS in the context of heteroscedasticity has a straightforward interpretation as weighted square estimator, and this is the last slide for today. So look here, it summarizes everything again. I'm in the linear regression model. The assumption is now that omega is some positive matrix. So far I know what omega is. Not surprisingly, next slide would be what it's not. And then I can find these prime matrix via the Gillespie decomposition, and I can derive the generalized square estimator. I can show that it's unbiased. I can show that it's consistent. It's asymptotically normal. And here it's a covariance matrix to derive. And it's efficient because, well, the proof of the efficiency of the GLS estimator is equivalent to the proof of the Gauss-Markov undercutting assumption simply because we modify the omega model into the testing assumption model. Right? So this is straightforward. Thank you very much. And next week, 19th September, are you here? Oh. You too.